All right, welcome to section 6.4, vectors and dot products. This video will cover examples 1 through 4 in your notes. You'll learn how to find the dot product of two vectors and use the properties. And you'll find the angle between two vectors and determine whether the vectors are orthogonal. So far you've studied only two vector operations, vector addition and multiplication by a scalar. So given a vector, you've been able to multiply in some number to either stretch or compress the vector. In this section, you'll study a third vector operation. It's called the dot product. It yields a scalar. The scalar is just a fancy word for a number, and it is not a vector. So before we begin, let's talk about what the dot product of two vectors looks like. So we've got two vectors, u and v. In order to find the dot product, you take the horizontal components, so u1 times v1, plus vertical components, u2 times v2. This yields a number, not a vector. So a couple things we should look at is the properties. So if you've got u dot v, it's the same thing as v dot u. So order doesn't matter. 0 dot any vector comes out to 0. Number 3 says, if you've got two vectors being added together, dotted with a third, you can take u dot v plus u dot w. Number 4, if you've got a vector and you're dotting it with the same vector, you actually get the magnitude of the vector squared. We'll look at an example of that in just a minute. And finally, so if you've got two vectors being dotted together, multiplied by some number out front, you've got c times vector u dot v, or u dot c vector v. All right, so let's take a look at some examples here. So just find the dot product. So we just take the horizontal components, multiply those together, so 8. Add together the vertical components, 15, so we get 23. For B, multiply the horizontal components, add the product of the vertical components, we get 0. And for C, multiply the horizontal components, add the product of the vertical components. Looks great. Looking back at this previous property though, number 4, v dot v. Let's take a look at a quick example. So say we've got, I don't know, 3, 4 dot the same vector. Now if we were to draw this vector, it'd be over 3 up 4. And we can see that the magnitude of this vector is 5. Now if we dot these together, multiply the vertical components, 9, add together, add that with the product of the horizontal components, and we get 25. So here, if we square that, we get our 25. Now what if instead it were, I don't know, -3, -4, dot -3, -4. So we'd be in the third quadrant, -3, -4. The magnitude would still be 5, but when we dot these, there's +9, +16, we get 25, which is the magnitude of this vector squared. All right, go ahead and try exercise 7 in your notes now. Check your answer in the back of the book. Come back when you're done. All right, in example 2, we're given that u is the vector 1, 3 in component form, v is 2, -4, and w is 1, -2. So we're using the properties of the dot product to find the indicated quantity. So in A, let's see, I've got u dot v. So if we dot those together, we've got, let's see, -2 plus, multiply the vertical components together, -12. And vector w is 1, -2. Remember, when we take the dot product, we're getting a number. So in this first quantity, we've got -4 times vector w, 1, -2. Simply distribute that -14, and the result being -14, +28. Box that answer. For B, we've got u dot 2v. Well, let's start here with the 2v. So u, of course, is -1, 3. 2v would be, let's see, double this. So 4, -8. Dot those together. So -4 plus the vertical product, -24. So it looks like -28. And for part C, they're asking us to find the magnitude of u. So u is -1, 3. So the magnitude of u, because it's in component form, is just the horizontal component squared plus the vertical component squared. So we've got 1 plus 10, looks like the square root of 10. Another option for doing this is we know that u dot u is equal to the magnitude of u squared. Well, u dot u would be -1, 3 dot -1, 3. So that would come out to, let's see, 1 plus 9. So the magnitude of u squared is 10. So taking the square root, we get +10. Two ways to do that problem, not picking on which way you prefer. All right, given u, v, and w, go ahead and find the following dot product. I would probably work from the inside out. Find what 3w is, dot it with v, and then multiply this number, which will be the result inside the parenthesis, by vector u. Check your answer in the back of the book. Come back when you're done. So say you've got two vectors, u and w. They're both non-zero vectors, so they have some length in some direction. And they're both in standard position, meaning both of their initial points are at the origin. So the angle that is between these two vectors, theta, can be found using the dot product. So the formula that we have is the cosine of this angle between the two vectors is equal to the dot product of the two vectors divided by the product of the magnitude of each vector. All right, so let's try example 3 together. So it's asking us to find the angle between u, which is 4, 3, and v, which is 3, 5. So we're looking for this angle theta here between them. So applying our formula, good mathematicians always start by writing down the formula they're going to use. U dot v divided by the magnitude of u times the magnitude of v. So I'm going to do a little side work over here. The magnitude of u is equal to, let's see, 4 squared plus 3 squared comes out to 4 squared is 16, 3 squared is 9. So the magnitude of u is square root of 25 or 5. Whereas the magnitude of v is equal to, let's see, 3 squared plus 5 squared. So it looks like 9 plus 25 looks like square roots of 34. So plugging in some values, we've got cosine of some theta is equal to the dot product. So multiply the horizontal components, 12. Multiply the vertical components, 3 plus 5 is 15, add those together, divided by the product of these two magnitudes. So 5 times root 34. So cleaning this up a little bit, we've got 27 over 5 root 34. So remember, we're looking for the angle between them, so theta equals some number. So now we grab our calculator and take the inverse cosine. So switch the arguments, 27 over 5 root 34 equals theta. So grab your calculator and type in inverse cosine of 27 divided by 5 root 34. Ooh, I got a domain error. Something weird is going on here. Let's go take a look. So go to figure it out. So it doesn't like something on this line right now. Well, order of operations says it's trying to find what's 27 divided by 5, get a number, and then multiply that product by square root of 34. And if we remember from chapter 4, the domain of the inverse cosine is from 0 to pi. So this result is larger than pi, so it's giving us an error. So to correct this, let's put parentheses around everything in my denominator. So open parentheses, 5 root 34, enter. Great. Looks like theta is 21.2 degrees. All right, go ahead and try exercise 23 in your notes now. Make sure you start by writing down the formula you're going to use. Do some side work to find the magnitude of U, the magnitude of V, and what is U dot V before applying the formula. Check your answer in the back of the book. Come back when you're done. All right, at this point, we know that cosine of theta is equal to U dot V over the magnitude of U times the magnitude of V. Now, if we cross multiply, we can see that U dot V is equal to the magnitude of U times the magnitude of V times cosine of theta. Now, thinking magnitudes, U and V are always going to be a positive number. Think hypotenuse of a right triangle. So with that in mind, if this is a positive number, whatever cosine is will dictate whether U dot V is positive or negative. If cosine is positive, a positive times a positive means U dot V must be a positive. But if instead if cosine of theta is negative, a positive times a negative means U dot V is going to be a negative. So let's look at one interesting scenario to see how this pans out. So let's say that our theta is 90 degrees. So we know that cosine of 90 degrees is equal to 0. So regardless of the magnitude of U or the magnitude of V, cosine of 90 degrees is 0, so U dot V is 0. This leads to a very important conclusion. Two vectors are said to be orthogonal if and only if U dot V is equal to 0. Now, the terms orthogonal and perpendicular mean essentially the same thing, but they meet at right angles. Even though the angle between the 0 vector and another vector is not defined, it's convenient to extend the definition of orthogonality to include the 0 vector. In other words, the 0 vector is orthogonal to every vector because 0 times any vector is equal to 0. All right, so here in example 4, they're asking us, are the vectors orthogonal? So do they form right angles? So U is 2, negative 3, V is 6, 4. Well, looking at them, they do appear to be orthogonal, but they're orthogonal if U dot V is equal to 0. So find the dot product, multiply the horizontal components. So 6 times 2 is 12, plus multiply the vertical components, so negative 12, comes out to 0. So because the dot product is 0, we can say that U and V are orthogonal vectors. All right, go ahead and try exercise 43, apply the dot product, check your answer in the back of the book, come back when you're done. All right, go ahead and try the wrap up for 6.4, examples 1 through 4. And number 1, you're just finding the dot product. For number 2, it looks like you're finding the dot product, which will be a scalar number, so a number, times a vector. So you should come up with a vector. When you get to C, remember that u dot u is equal to the magnitude of u squared. So if you find the dot product, you can just take the square root. Number 3, apply the formula. And number 4, check the dot product. If it's 0, they're orthogonal, and if it's not 0, they are not orthogonal. Come to class with questions tomorrow. I'll see you soon.